the video is uploaded. I forgot to post the playlist. I'll post it on the syllabus, but it's uploaded. If you want to check it out for sure, you know my YouTube channel, so it's there. Basically, everything I uploaded is in that channel. You can always check out the SysSkill lecture as well as the other classes lecture as well, including this one. And today we'll actually move on and do a quick recap on some of the things from lecture one that I want to make sure you are aware, right? On Tuesday we talk actually we spend a lot of time talking about the history, trying to see the context on where we are in terms of one of the oldest field in computer science. Like basically nothing is possible without an actual computer, right? So we built the actual hardware, make it possible to program, make it possible to store data, make it possible to run things like parallel program. I hope you find it fun, and I hope you find it at least like looking into a different perspective of stuff that not a lot of people talk about, right? Especially in Thailand. And now we're going to a deeper look on the ISA, right? But before we do that, let's do a quick recap. So on Tuesday, we talk about what is a computer, right? So basically, there's a processing element, there's a memory element, and there's an I/O element. So my cat is fighting element somewhere. Sorry. And then we also said that when you have data in the file, right, they get transferred over to the memory, both the program and the data, and they get run, right? So this is the processing part. Also cat trying to steal my food. And we talk about the von Neumann model, which is a store program computer, right? What does it mean? From our system skill class, we know that program, when you actually double click to run, or when you actually hit enter in the terminal to run the program gets stored, basically being transferred. The binary is transferred. The OS schedule, right? Now that you did the basic OS, they actually run the program. They are the one that manage all the tasks. They are being put into the main memory. That's when we start running, right? And there are two key properties of the von Neumann model, which make it really, really nice program. The instructions are stored in the linear memory array. When we said linear memory array, that's like a ancient terminology. Basically, it's a linear memory, DRAM, right? One dimensional, right? From address 0 to address, depending on your size, 10,000, 10 million, 1 billion, right? The memory is unified between instruction and the data. What does it mean? It means that we have to kind of manage it somehow. Oh, this is a program. I'm going to interpret it as a program. When I want to load the data, that's a region where the data belongs, right? And we have this nice sequential instruction processing, right? Sequential instruction processing. It means that we run one thing at a time. Simple, right? One instruction at a time. We fetch the instruction, which means that we take the instruction from the memory, look at that instruction. Oh, okay, this is the instruction supposed to do an add between this number and that number and produce the results. Execute it and complete it, right? The program counter identifies the current instruction, and it advanced sequentially except for the control transfer instruction. What does it mean? If else, for loop, anything that is a branch in your code. Why do we call it a branch? The code typically go one way. When it branch, it means if go there, go here, else go on to the other path. That's it. That's why we call it a branch, right? And that's for the recap. I want you to get out of the lecture on Tuesday. Again, it's a lot of side topics. We talk about a lot of our history. Hopefully it's lighter. Hopefully it's more interesting. And hopefully you don't have to memorize anything there, right? But now here come things that you might have to consider / memorize a little bit, right? And by memorize, I'm not telling you to memorize a lot, to be honest. I go into computer science and computer engineering expecting that I don't have to remember things, which is still hold true compared to biology or medical area, right? So the question that we have is, we have a hardware, transistor, capacitor, right? We have to be able to talk to them, not literally in the say that I can face my desktop right here and say, run this program, and it will run, right? I guess you can do it with the Alexa. Oh, not too loud, otherwise it would actually try to listen to what I'm saying here. But you can order these devices to do certain tasks, right? And when you program, think about it this way. You basically have to communicate with the computer saying, hey, do this task. And computer, the only thing they understand is high voltage, low voltage. It's a piece of electronics, right? So you only deal with electrical signals. And back in lecture one, we kind of established also in system skill, right? High voltage, one, low voltage, zero. It can be the inverse, who cares, right? High voltage can be zero, low voltage can be one. The same thing, binary number. This is why you want to use binary. It's really easy to differentiate between high voltage and low voltage, right? The idea is, right, let's represent our human instruction in binary format, right, where the command are in binary, data are in binary. So what is the most basic element that you have known so far that translate a letter into binary? Can someone tell me an example of that? I guess yes and no can be 0 and 1. Okay, I didn't expect that answer, but that's an awesome answer, right? You can convert bits into a character, right, through what we call ASCII, right? A sequence of certain bits would mean the letter capital A. Another sequence would mean the letter capital B, right? So why can't I do the same thing? If I see this sequence, it means I want to do an add. Can anyone here remember our old friend assignment 3, the disassembly part? The Q thing that you have to do pop and push? Remember that? Same concept there, right? Same concept there. That's how we can talk to the computer. Basically, by default, we can say, hey, if you see this pattern, it means I want to do an add, and I want to add this register with this register and produce the result, write it back to the other register, right? And this becomes the interface between assembly code and the computer, right? Now you have the assembly code, which relatively look human readable. I don't even want to finish that sentence because whenever I say assembly, I bang my head at the wall, right? It's not easy to understand assembly, but it's still better than ones and zero. There's a way to convert assembly into ones and zero, right? The ISA versus microarchitectures, the difference here is the ISA, or instruction set architecture. It defines a list of commands that the microarchitecture can understand. Think of microarchitecture as the hardware pieces and the features that come with different hardware, right? And the ISA is what the programmer can do from the assembly point of view, what the programmer can do to actually utilize the hardware. So that's the difference. The hardware itself and the ability to control the hardware. The ISA provide the ability to control those, right? The microarchitecture is the actual hardware that allows the circuits to perform each of the commands. These particular microarchitecture features would allow you to do multiply add, right? these would allow you to do matrix multiply, and we will call that neural processor for the fanciness of it. So we can say, hey, this is used for machine learning. These are microarchitecture, right? This is the design. The microprocessor, as we know it, is the combination of the two, right? Is microarchitecture alone useful? You can throw it's a brick. Basically, it's a brick. You can throw it at a wall, right? If we cannot really program that chip, it becomes useless. Without the microarchitecture, if we have the ISA alone, if we have x86, but we don't have enough money to buy an Intel or AMD chip, is that useful? Not really, right? You can't run anything because you don't have the money to buy your chip. So the microprocessor, as we know it, right, is the combination of ISA and microarchitecture. It gives you the full way to control the hardware. So today we'll focus on the ISA. After today, we'll focus on the hardware parts. But today we'll focus on the ISA for now. It stands for instruction set architecture. So the most important thing in there is obviously instruction, right? It needs to contain instruction. So anyone want to throw me some example of what is inside an instruction? What are the information that has to be inside the instruction? It should contain the name and the parameters, right? We call the name is the opcode, operation code. It basically determines what are you supposed to do with that instruction. Addressing mode, how are you gonna look at the data? The data type, is that an integer? Is that a floating point? Because the way you treat integer and floating point are different, right? The way you add the two binary would be treated differently. It should contain instruction types and format, right? It should contain, okay, is it add immediate versus an add, right? Register, obviously, and you pointed out, right? The register that has to be operated on. Anyone here know what condition code is? So let me ask you this. Would it be nice if I have an instruction to say, do this add only if the previous instruction results in a 0, or if the previous instruction results in a negative number? It can be useful, right? So if you want to make sure, for example, your assembly is really small. So tell me one benefit of having a really tiny code in assembly. Yeah, like switch case will work too. But let's say I have a really tiny code, right? What would be the benefit of that? Your code is small, your binary is small. So it's not exactly can always be fast, right? If it's small code and loop around a lot, it can still be long. Is it portable? It depends. But because they are small, it will fit in a tiny processor. And we have the tiny processor everywhere, right? Everywhere. Let me give you an example. My refrigerator right here definitely will have some processor to control the temperature, right? What would be the use of a fridge if I cannot control my temperature? Everything will go either too cold or too hot, right? Bad either way. My air conditioner also will have a small chip, right, to control the temperature. These chips are tiny. It's not your full-blown CPU. It's a really tiny chip. So with the tiny chip, it comes with a really, really tiny amount of memory. It means that you somehow have to write a code so small that fits in there, right? I'm pretty sure you didn't grow up with that memory that it's only a few kilobytes big, right? including myself. I grew up when the memory is a few megabytes when I'm young, like really young. And then when I'm like let's say 15 years old, it's like hundreds of megabytes. And then when I'm in college, we kind of move from 32-bit to 64-bit. We go beyond 4 GB, right? Imagine, let's say you have 16 megabytes of memory, and you need to fit both your instruction and data in there. Both instruction and data in there. It can be challenging, right? It can be pretty challenging to make sure to write a program that fits. So condition code determine these different instruction add if the previous instruction result in 0, multiply if the previous instruction is a negative number. Right? This can make your code size smaller. Fun fact, that's why ARM originally is actually have this condition code and this what we call predicated execution, which has the add if 0, add if negative. It worked so well with embedded processor. And I hear a cat. Definitely not from my speaker. Memory should be kind of specified in the ISA. Why? When you buy DRAM, what you're getting is basically, so to minimize echo, I will make sure. Do you mind if I mute your? Be mute. Oh, here. Wait. I cannot mute. It's magic. What? Okay, so it's not too bad, I hope, the echo, but for some reason I cannot mute you. Uh even though I'm a host, that's weird. But if you look at the main memory, right? If you look at the main memory, what you say is correct. You need a way to manage virtual memory, right? You need to manage your DRAM. When you buy DRAM, what you're getting is a flat address, one-dimensional address. Think of it as a piece of land with no control, right? So imagine, let's say you're thrown into a country with a bunch of land and no one have any control or any rule on how do you occupy the land. Imagine how much chaos would that be, right? You might end up, I guess, killing each other. Don't do that, guys, to occupy someone else's land, right? Because there's no rule, right? So the ISA have to govern that. It do have to actually figure out how do I manage the address space. Basically, these are the law that is described in the ISA on how each program and each addresses should be treated in terms of the who owns what, who can access what, right? Addressability. Do you want to access every single bytes, every single 4 bytes? Alignment. Are you allowing this weird 4 byte access, but on the third byte and on the second byte, instead of having to make sure everything is fully 4 bytes aligned or 8 bytes aligned, right? The ISA will tell that. Some of them will allow this. It would make the design more complex. Will make the program more flexible. Some of them will not allow it and make the hardware simple. The program have to, when you program in assembly, it will be a little bit more complicated. So that's a trade-off. Virtual memory management. How do you make sure no one can touch whatever you own, right? It also specifies how do I handle system call. Are you sick of it right now with the OS parts? How do you handle interrupts? How do you handle exception handling? So whatever you learn in the OS part, be aware those are for x86, and that can change based on the ISA. But a nice thing about it is the way you think about it is applied everywhere. You just need to change the syntax in most cases. ISA, think of it as the law for this particular chip. You have to follow this law, otherwise you get kicked out. Well, it won't run, basically, right? So it will determine how do you call functions, how do you handle interrupts, how do you handle exception, how do you handle access control? Are you going to boot that program out? How do you handle priority? Who get the privilege? How do you interface with the I/O, right? Input and output, which is basically anything governing the hard drive, keyboard, mouse, monitor. Threat management, hopefully you're sick of it by now. Oh, I don't hope that, sorry. But I feel like you're sick of it by now, right? Threat management, the ISA would specify how does each threat being managed in the hardware and how should the software manage it. Power and thermal management. Surprise, you can control power. You can control the temperature of the chip. You can make it low power, right? So hopefully device lasts longer and don't have to recharge your battery. So the ISA actually have that element too. All right. And for the microarchitecture, think about it as ISA define what the software can do. The microarchitecture implement everything in the ISA. Let's say you have an ISA that promise I will have an instruction that do a quick sort. If I call this instruction, it will perform a quick sort for this range of address. It means that the hardware guy basically say, okay, I need to implement quicksort. Basically, I need to implement that functionality, right? There are multiple ways you can do this. You can kind of break it down to smaller instructions. That's also fine, right? We call this microcode. We are not going to go into that detail. If you're curious, let me know. The key idea is the hardware need to follow the ISA as well. The software use the ISA as a tool to program the hardware. The hardware implements everything that's specified in the ISA, right? The design itself can come with a bunch of trade-off, right? I can build an adder that takes forever, right? It's fine. I mean, it will add eventually. Is that a good thing? No, right? I can build an adder that's blazingly fast, right? And one thing that you have to know is everything in the microarchitecture is transparent to software. Things that we're gonna learn today and things that we're gonna learn in the next actually quite a lot of lectures until the end. These are not programmable from the software point of view, but this is how the hardware run. So if you know exactly how it runs, you can avoid things that make your program slow, like branch if else, something like linked list versus an array, right? Array is actually faster. There are certain reasons behind it from caching point of view, right? So things like pipelining, which you'll learn in I think 2 more lectures, in order versus out of order, we will not learn this. This is for the architecture class. Memory scheduling, also we will not learn this. But fun fact, when you send a load and store to your DRAM, there's another controller that figure out who get to load first. Okay. You never know about those things, right? You cannot control it. But it's features that come with every chip. And hopefully the goal is to make everything as fast as possible. Make it as fast as possible. Branch prediction. When you have if else, the hardware actually predict, are we going to the if or are we going to the else? It actually do that prediction for you. Speculative execution. You actually run the code ahead, actually. So these days your chip can run ahead of time from the line that you're running so that you get the data back if you can actually get those data. It makes things faster, right? Superscalar, it means that you can run more than one instruction per clock cycle. You have, let's say, 4 adders. So I'm going to fill in using all the 4 adders, right? I'll identify instruction that can utilize all this adder and I'll apply them all. I'll add 4 things at once. Dynamic voltage and frequency scaling. I test the program. It's too fast. Basically, I don't need it to be that fast. I'm gonna slow it down so that it uses less energy. I'm gonna clock things up to make it fast. Anyone here heard about turbo boost? I think I asked this question, right? Last lecture. This is what turbo boost is using. Anyone heard about this uh thing? I think it's became a Apple lawsuit, right? That say, hey, Apple suddenly make my chip slower when the battery is not really good. Anyone heard about that? I think it was something in the news, I think 2 years ago. I have to tell you a fun fact, everyone did that. Intel do that, AMD do that. It's like a default. This is basically textbook dynamic voltage frequency scaling. Do you want your battery to drain in 3 hours or do you want your battery to drain in 6 hours? You probably want the latter, right? The lawsuit basically look at the wording like, oh, you need to tell the user that hey, it's not as fast as before. Yeah, obviously, right? So just be aware these things are done. Error correction. So if you deploy your code in a server, right? What will happen if the server crash? So it's bad. Basically, you're gonna lose money. So it's bad. So many of the like server grade machine comes with the DRAM that can correct error. Why is that the case? How many of you here run into blue screen? Everyone, right? Those some of those come from random bit flips inside your memory. It actually can come from that, right? Random gamma particle can hit that particular capacitor, flip the bit because electron just happen to be energized and bump out of that capacitor. Physics, high school physics, you give energy to an electron, it moves, right? So with that, you can actually do tricks to the way you organize the data so you add more bits to correct this error. This allows the server grade machine to avoid blue screen and reboot randomly, right? So this would help when you have to host really like sensitive application that you don't want it crash, essentially. So these are the microarchitecture. These are the hardware design that are being put in to make things either faster, more reliable, save power, save the cost, right? So what are the trade-off? It means that if you want performance, you probably have to pay more. If you want more reliability, you have to pay more. If you want cheap things, it means you have to sacrifice something, right? For example, anyone hear about this particular data format that somehow NVIDIA PR and marketing team that's like, oh, we invent new thing called TF32. Whatever heck they call TensorFlow 32. Which is a really bad way to name things, to be honest. So how many bits do you think TF32 takes? You think it would take 32 bits, right? If I'm looking it up right now because I kind of forgot, it actually takes 18 bits. It is a trick question because this is, I'm sure this is done by NVIDIA PR team and me as an engineer who basically work on GPU architecture. I absolutely hate this. What they're doing is I'm going to reduce the accuracy. So remember our system skill day, we have floating point, right? We have this exponent bit and mantissa bit. And the mantissa kind of determine how accurate the number is, right? And because you do machine learning, you can afford to be a little bit not as accurate. But that's fine. So they say, hey, let's cut those bits. And that's it. That's TF32. So this is really, really, really misleading, right? But yeah, it's a design trade-off. Is it good? Actually, yes. Anyone want to guess why this is good? Well, except for the confusing part about like PR, basically. It's likely to take less time to access because you're not involving the whole 32-bit bits, right? You can store more data with the same amount of memory. That's awesome. Basically, that's one of the key. You can actually pack, you can actually pack more things into one word, right? So it ended up more throughput, which means, as you said, it can train things faster without likely not any accuracy trade-off, right? So you can have a as good model, but faster. You can train more things, basically. And one thing you know about deep learning is the more data you train, the more accuracy you're going to get. So if you can train more data with the same amount of time, what does it mean? I will have a better model, right? I am likely to have a better model. So that's why they came up with the idea that, hey, let's make it less accurate. You can have different number of register. To be honest, today we'll work with the MIPS ISA. It's a totally different ISA, not x86. The reason why I give you this ISA is much, much, much cleaner than x86. It contains mostly the basic instructions, everything built from there. You're not gonna have this like 500 pages white paper on how to use each instruction in the MIPS ISA, similar to x86, because there's so many instructions, right? Number of register in each ISA also gives you trade-off, right? Think about it. Simple. If you have 16 register, it's going to be easier to program than 8, right? But it also requires more hardware to implement 16 versus 8. That's it. It's as simple as that, right? The number of ports to the register files. What does port mean in real life? What is a port? It's where thing connects, right? It is where, like in real life, a port is where you have one thing that carry a lot of stuff and you transfer it to another entity, right? A place to park your boat, Taria basically, right? Is where you can transfer goods, right? A port is where you can transfer the data. So if you have more ports, what does it mean? I can access things in my register files more at once, right? So I have, if let's say I have 4 ports, it means that I can do 4 data transfer at once. If I have only 1 port, it means that every chip has to queue up, right, to transfer those data. So the number of ports to the register files also impacts performance. The number of cycles to perform one multiply is another thing that is inside the microarchitecture, right? So this is the element of the ISA. This is the element of microarchitecture, right? Because the floating point is, oh, actually bit pattern is the ISA. My bad. The ISA determined TF32 means using 18 bits. The first two is the ISA. Number of port is the microarchitecture because you basically implement it in the hardware. As a programmer, you don't really notice that, right? Number of cycles used to perform one multiply is also microarchitecture. It's just how you implement your multiplier, right? The way you multiply in the program will be the same. I put in the sign that looks like this. It's a multiply, right? Every language knows that that's a multiply. In assembly, you say MULT, multiply, right? The how long it takes is the matter of the microarchitecture. How good am I at building the multiply? So what happens if there is a change, right? So let me ask you this question. So what's the most common language spoken in the world right now? We'll say global language. Meme. Good. All right. Let's say it's English, right? So let's say it's English. Uh, so let's say English is a common language. And let's say that's an ISA. It's an ISA for me to communicate with everyone, right? I can kind of assume-ish that if I go to most country and if I use English, I can roughly survive. Not exactly sure about going into China, but you probably manage to like buy things, get food, and live, right? But what if I say, hey, the global language changed, and somehow everyone needs to use Thai? Yeah, there's going to be a lot of miscommunication, right? You have to reprogram almost every human on Earth, right? So, how many of you here use the M1 processor from Apple? Anyone at all? So, if you talk to someone who has this new MacBook that uses the M1 processor, you can ask them how's Rosetta and how's like cross compilation. Because most of the software would be good, but some of the software are not as easy to like make sure everything still works the same way, right? I see a passionate yes. So I see a passionate yes. So it can be painful in some cases, right? Because M1 processor trigger the ISA changes. Many programs are done in x86. So Apple software has been running in x86, and it's a pain for you to install Node.js, right? Because it's not designed for ARM originally. It will take a few years, to be honest. They are going to write a program to make sure it compile in ARM ISA really well, right? It is a pain to use anything really, I agree. But in a few years, they'll adapt for sure, right? But think about it this way: when you change the ISA, it means that somehow you're forcing me, say, a guy who know how to talk in Thai-ish and English. I can talk in these two languages and roughly communicate, even though sometimes I speak nonsense, right? But then you're throwing me into a room of people that say speak German and doesn't know English or Thai. That's when the ISA changed, right? The program without the source code will stop working. The program with source codes will need to be recompiled and re-optimized. Compiler need to be re-optimized for the new ISA, right? So if Apple, for example, did a good job with this process, you can cross-compile. You can also change the instruction from x86 to ARM. So you can get by with that, but you need to basically make sure that exists, right? So Rosetta is a code transformation. Basically, it transforms executable of one ISA into another one. And as those of you who use the new MacBook with the M1 chip, it's a pain to use anything, really, right? So as I said, this will take time. if you need to change the ISA, is so much of the overhead, and also that's one of the reasons why people keep using x86. Also, fun fact: anyone here heard about IA64? But you all know about 64-bit, right? So there was a time when we'd have to transition from 32 bits to 64 bits. So Intel and AMD were racing to see who come up with the ISA for 64 bits. AMD worked with the what we call AMD 64, which is an extension to x86 32 bits. IA64 add a lot more fancy instructions actually, but there's a compatibility issue. So what does it mean? It means that the program that works in 32-bit Intel ISA will not run on IA64. So imagine between these two, which one wins? Yep, AMD 64 won. So actually, if you buy Intel chip these days, they are actually using AMD 64 ISA, right? So don't get confused when you download. Oh, this one is AMD 64. Yeah, that's it. That's the 64-bit chip that you've been using. Oh yeah. So the question is you confused about the IA64. IA64 is the 64-bit attempt from Intel. They say, hey, let's change the ISA. It's elegant. It's nice. The only problem, it doesn't have the backward compatibility support, which means that if you buy a chip and download a program that only works with the 32-bit instruction set, that program will not run. But if you use AMD 64, it can still run. So which ISA will you buy? Let me just ask that one question. Which one do you buy? The AMD, right? Because I can run the older version of Microsoft Word. I don't want to buy another version. It's already cost me so much, right? So that's why. You have to consider the effects of changing the ISA, right? So the conclusion here is what? You don't want that many ISA. Unlike the web development and its framework and the language that seems to come up like one or two popular one each year, you don't end up with that many ISA, right? You have x86, you have ARM, you have Power. Power is used in the IBM cluster, right? And then you have RISC-V, which is another open ISA, and that's it. Basically, that's a common one, right? Uh, and here are some of the trade-off, right? So imagine, let's say you have the ability to define your own ISA, right? This is something you can do as a engineer, right? Oh, so that's a question whether is it possible to make more than one ISA in the same device? I guess theoretically possible, but will be super annoying because it means that you have to support every instruction in both ISA. Every instruction in both ISA. And if they have the same bit pattern, how are you going to differentiate between the two ISA? Is it the one for ISA 1 or ISA 2? Is this an add or is this a jump if this is true? Right? So that's a problem. Right? That's a problem. So it's gonna be super painful. So that's why I said theoretically, I guess you can engineer so that it exists, but it's gonna be not useful. Right? It's not gonna be useful because and you can't just simply add another bit too. Because what will happen if you add another bit? It means that this program will not work on that ISA anymore. You change the ISA, right? Uh, so the trade-off is each ISA comes with different complexity. Compressed ISA. So a compressed ISA is possible. It depends on how you're gonna treat the compressed format, right? So basically, if you have to make your code smaller and smaller, I guess you can compress it. And you uncompress later when you have to actually process the instruction. Sometimes different ISA come up with a shorter version of the ISA. For example, ARM has the 32-bit version, 16-bit version, and that's what they call a thumb, which is a part of your ARM, basically. That's 8 bits, right? So the 8-bit one would be really useful for the small microcontroller in your refrigerator or your air conditioner or your, I don't know. I was about to say TV, but these days TV is full blown like a computer, so I can't use that, right? But ARM instruction and thumb instruction, thumb would run on ARM ISA. You can switch from ARM to thumb mode, right? You can switch between the two modes. That's a way to call so that it switch between the two. And again, this is awesome. This is a way to actually have a fun discussion, right? And the trade-off also is how do you specify each of the instruction, right? Because the assembly code for each of the ISA would look differently. If you look at ARM versus look at x86, you see the difference. You likely can guess what it's doing. They'll use the same word. Add means add, multiply means multiply, right? But there might be some weird instruction that's built in to do fancy things, right? You can support certain features in some ISA. They might have multi-threading support. Most ISA these days have multi-threading support, right? They can support a lower power version in case you want to have an embedded processor. You can support a lower amount of memory, right? To make it really efficient, let's say you only have 10 kilobytes of data to work with. You can support what we call really large, very large instruction window, which is basically means that I can schedule multiple instruction at the same time, right? The ISA can support that. SIMD, which is kind of like one of the core bases of the GPU, is enabling through the ISA. Intel chip can do SIMD as well, right? It's called AVX instruction. And you can run something that would kind of resemble what is done on the CPU somewhat, right? The ISA can support both SIMD and fine-grained multi-threading, which is the GPU. The way GPU run things you would have to enable both of them, right? And the type of ISA can be categorized into generally two big bins. Have you heard about the CISC versus RISC at all? CISC come from complex ISA. RISC come from reduced ISA, right? Complex ISA means that my instruction set architecture will support many fancy operation. I might even have a instruction that do sorting. I might have an instruction that do a matrix multiply, right? I might have an instruction that would perform a loop until these register becomes 0 or something like that. So it contains many instructions. What would be the potential downside of a CISC ISA? Large, right? The hardware implementation can be really complex, right? It can be complicated. And there's another question about like, what about the code size? If I have a lot of instruction in the ISA, would the code size become big? Depending on how many bits each instruction would take, right? And how do you process all the bits? So that kind of depends. That depends. But for a reduced instruction set architecture or RISC, it will contain the basic thing: add, multiply, branch, jump, syscall, right? And that's it. That will be really clean, easy to implement, you can optimize your code a lot because, I mean, let's say you detect a loop, right? So you can optimize things in there. So it means that there are trade-off between CISC and RISC processor, right? The CISC processor will have fancy instruction. And yes, as you said in the chat, it can be a lot faster because it has a lot of specialized instruction. That is true. That is totally true. But people who do, or I guess there was a war between which one was better, right? And people who argue that RISC might be better is, instead of focusing on these instructions that do really, really specialized things, why can't I use this area on the chip for something else? What if I have a bigger cache? Because I don't have to support this whole hardware design for matrix multiply anymore, right? So I can dedicate the chip for branch predictor, cache, basically fancy way to support more processor, right? I can have even more processor here. So I can make it faster that way. And is there a right solution? I don't think so, to be honest. Everything is about trade-off, right? Everything is about trade-off. And the right design, eventually they have to be evaluated by running real program, right? By running real program. So now that we talk about the ISA, let's talk about the core thing, the instruction. This is the most basic elements of the interface between the program that you write and the hardware, right? And as I said, the main component is opcode and operand, right? We've been talking about this since the x86 lecture part on system skill. The opcode is telling what is that instruction. The operand is who is being operated on, right? The data at this address or the data at this register. For example, let me write a really, really generic ISA. I don't even have a definition for that, but if you look at it, you can guess what it does. Add R0, R1, R2 can mean that I'm gonna add R1 and R2 and then write the result into R0. And in this case, the plus sign is the operator. R2 and R1 are the operand, as well as R0, right? So let's go back to the element of the ISA, right? You can look into the sequencing model. So this has to do with the von Neumann versus data flow architecture, right? So we'll focus on the control flow sequencing model for now. But you can make it data flow too. But we're not going to talk about it. I'm just saying here because they exist. They exist. Most of the programs so far use control flow. It has jump, it has branch, it can support if else, it can store data, it has states. It also has what we call processing style, right? How many operands are in the instructions? You can have 0 operands, 1 operand, 2 operands, 3 operands, right? And so far, I've seen up to 3, basically. So zero address machine is basically a stack machine. You have a stack, you can push something, and then you can pop. Pop means I just take it out, do something with it, done. So I can have a 0 address machine, which is just a stack. Push things to store temporary results, pop to perform computation. You can have one address machine, which means I can now specify one address. What can I do with one address? I can accumulate, count up, count down, right? I can count up, increment, decrement. I can load the data and can store the data to that address. 0 address and 1 address machine are just basically not that useful if you want to think about it, but they exist. They exist. Most modern machine, if not all, would have either 2 address or 3 address machine. So for x86, anyone wants to take a guess which one is x86? Remember our assembly lecture? Look at the add instruction and look at which one is this. Is it to address or three address? It's actually to address because you have the add, right? Say add EAX, EBX. This means that I'm gonna add EAX with EBX and write the result back to EAX. Right? So this is two address machine. A three address machine would say, I can do this. Add source one, source two, and destination. Much more convenient, actually, right? So now you might be wondering, so what are the trade-off of these like addressing style, processing styles? How compact can be, right? And the number of operation, basically, the number of operation. Sometimes if it's two address machine, you might have to write two lines to do the same thing, right? With the zero address machine, you probably need to write 10 lines, 10 lines to do the exact same thing as one instruction in the three address machine, right? What else? Oh, same slide, my bad. Instruction, right? Operand specifier, which is the addressing mode, right? And the data type, this is as simple as it's an integer, floating point, character. So why is it important to be able to differentiate between an integer and a floating point? Can someone tell me why would I care about that? So how do I add to integer? I add an integer. So just add a floating point. I did the same bit operation. If you think about operating into bits operation, are they the same exact operation? They're not, right? Floating point is actually way more complex because you need to calculate the exponent and then multiply by the mantissa and to just get the number before you can add, right? So adding a floating point number is way more complex compared to adding an integer. So you need to tell the hardware that, hey, this is an integer. So when you do an add, it's add on an integer. Otherwise, it's an add on the floating point. Some ISA even support complex structure, such as WAX, right, or x86. These has a lot of fancy instruction that support common complex structure. So another thing is the complexity of instruction can vary. For example, if I know I'm going to build a chip to do signal processing, let's say I want to build a chip that goes into the audio processor, right? I'll have to do a lot of signal processing. I have to do a lot of Fourier transform, right? I'm not sure if you how familiar you are with the Fourier transform. Basically, it's transform a signal from a time domain into a frequency domain to do a lot of signal processing. You need convolution. So it might be a good idea to build a complex instruction that do convolution for you. In ARM processor, there's an instruction that you kind of can load an entire array, right? So these are pre-built in the ComSysArch. For the simple instruction like add, XOR, load, and store, those are exist in both RISC and ComSysISA. But the complexity of the instruction is your choice. When you design an ISA, it's your choice. You can do whatever you want. You can do whatever you want. It's like you get to make a law and then everyone has to follow the law. But then at the same time, you have to basically make a good law, right? Otherwise, we ended up with some chaotic country, right? So that's how you design the ISA. That's the rule that govern both the hardware and the software. So you need to think carefully what you want to add because that is the law. You can't just randomly add laws to like do weird things. It's gonna be a waste of resources. right? And quick note, basically with simple instruction, you can always build complex instruction from it, right? So that's one of the trade-off. So here's the benefit in a high level. So let's say you look at x86, right? So you're gonna have smaller code size because if you know you want to do this certain task and there's an ISA exactly instruction for that, one instruction done, right? So your code size is likely to be smaller. The compiler is likely to be more simple, right? I look at the code, I map to a certain instruction, that's all. For reduced instruction set, the hardware is going to be simpler to design, right? It performs only simple instruction, which means that there's a high likelihood that I can clock it really, really fast. Because adder is simple, so I can clock this to, basically I can clock it really, really, really fast. And you can do a lot of compiler optimization because you ended up will have to compile until you add, multiply, and subtract and everything, right? So it gives the opportunity for the compiler based on different hardware specifications. So that becomes the risk versus CISC debate. And it's one of the debate I don't get involved with. It's almost like if you are debating someone whether you want to be a Buddhist or versus Christian or like going to Islam, right? It becomes a religion these days. But the key things here is risk is simpler. The compiler can optimize code and no fancy instruction. An example of a machine that uses risk, as you can guess, it's a lot of older generation machine, except for one thing here. RISC-V is the new thing. RISC-V is one of the new instruction set architecture being pushed aggressively, and I think there's a lot of great things from RISC-V. So if you look at our optional reading for this week, one of them is to look into why does the author of RISC-V come up with this thing? What's the motivation behind it, right? CISC, as you can see here, x86 is a CISC architecture. ISA, my bad. It's a CISC ISA. You can have fancy and complex instruction. For example, in x86, there's this instruction called repeat move s. Basically, it means that I'm gonna repeat doing the move instruction many times. Why do you want that? You can copy data from one array to another, right? Repeat moving everything in this array into another array. Loading the data from this array from the main memory into my register, something like that, right? Compiler can optimize code into different types of instruction, and you are likely to have smaller program size, right? So that's the debate between whether you want reduced instruction or complex instruction. The other debate is what we call semantic gap. So this is more relevant to you as a programmer. This is a gap between the program and the ISA, right? The program, as in like your actual code, to the assembly, right? So you can write an ISA with a large semantic gap. The assembly looks like put the signal voltage here high, put this voltage low, right? One example of that is look at the quantum computer right now. It has a huge semantic gap for the ISA at the moment, right? Instruction can control a set of control signal in the hardware, and the compiler somehow has to convert your C program, your Java program, your Python code into that. So there's a lot of work to do in the compiler if you assume that, right? And as a hardware architect, we'll probably get murdered by them because that's too much. Another side of things is, what if an ISA almost looks like a high-level language, right? It allows more application-specific hardware optimization, but then compiler cannot do much, right? So there's a trade-off here as well. Which one is preferred? And translation of one ISA into another ISA change the semantic gap. Semantics means the meaning inside your program. So when you change the gap, it's painful. That's why if you buy the M1 processor and use a program traditionally designed for x86, that's why sometimes it doesn't install, because there's a change in the semantic gap. And this thing can be done both in the hardware and or in software. Rosetta, which is Apple's attempt to do this, definitely a great attempt, and I'm sure they'll patch it so that it works. So this can be done. This can be done, right? That's why I said this part is relevant for all of you guys. If you buy an Apple MacBook that uses the M1 chip, be aware of this. I'm sure they're gonna patch it, but it can be annoying, right? Trade-off with different data type also comes with the ISA design as well. Sometimes you have the high level of data type and it gives you a lot of benefit, right? But there's also a downside of that because the semantic gap, data types are tied to the semantic level. For example, what if I declare a data type called linked list, right? In Scala, and Scala, if you took parallel programming, right? We learned a language called Scala. Inside there's this thing called linked list, right? So you can use linked list using that data type. It's a type, but then it also means that, well, I have to implement the type, right? It If you actually implement the type in the ISA, it closes up the semantic gap, right? But it also leaves a lot of room for, because the compiler don't have a job, basically. You can do what Scala did. The compiler figure out how to do linked lists, and then the hardware just operate with address and integer, right? So what else are the elements of the ISA? So I've been talking about the elements of the ISA so far. The other thing that are super important is memory organization, right? How do I control the number of unique location in the main memory? Basically control things like who can access what? Can I access every single bit? Can I go to every single byte? Or do I prevent them and make sure they just go at the word level, 64 32 bits, right? One exercise is, let's say you want to add two 32-bit number, but you only have byte addressability. What's the difference between that and, let's say I want to add 8 bits number, but I have 32-bit addressability? What does it mean? In the first case, right, I have 32-bit number, but I can only access this chunk at a time. So how many instructions do I ended up writing? Definitely at minimum 4, right? Add this, add this, add this, add this, and somehow take care of the carry bit. Somehow take care of the carry bit, right? So it's likely 4. That's likely to be support about like, oh, if the previous add result in the carry bit, make sure you add 1, right? Or make sure you increment, for example, right? So what about this? Let's say you have the machine that can add to 8 bits number. Oh, no. Machine that can add 32 bit, but you only want to add 8 bits. So you can add this entire thing, this is 32 bit. But in reality, you just want to add this A and B. So what do you do? Can you just directly add this two numbers together? So let's say this X and y. Can I just do x plus y and then mask that? Can I do that? So now what is likely correct, right? So you can't flat out add and mask because you're gonna end up with random carry bit coming from this side, right? Which would impact the results. So you might want to say shift, right? Shift and then add and then mask it out, or shift and then and to mask it out and then add them together. So it's not as obvious, right? You have to carefully think. That's why the element of the ISA, let's say you enable this and this and this. It's convenient, right? You can go into each byte. You can go into each 32 byte. You can go into each 64 bytes. So this is one of the common trend. You have different granularity enabled by the ISA. Virtual memory support is another important one, but this is basically kind of applied to the virtual memory lecture we've been talking about in system skills, so we're gonna bypass that. It basically tells, oh, okay, these bits represent this part, the page table entry has these many entries, it consists of these many bits. Most assumption we have in system skill on how many entries are in a page table, how many bits we are using, they will be specified in the ISA. Basically, they are being specified in the ISA. It will tell you exactly what each of the bits mean. Big and little endian also is one of the elements of the ISA. Some of them use big endian, some of them use little endian, some of them use a mixed version of big and little endian. Right? What else? Register. Think of register as a really fast memory. Takes typically one cycle to go and access. Right? How many do we need? And what's the size? Because that's also, again, trade-off. If you have more register, you burn the chip area. You need to implement them. If you have fewer register, then you might end up with more instruction, right? Oops, sorry. So this benefit data locality because if you need certain value more often, you put them in the register before you do the computation. And there's also an evolution of register. Back in the day, the only thing we can do with register is I add them up, right? So we call that accumulator. We call them accumulator. The only thing it can do is add, reset, add, reset, right? Imagine if you had a program using register that can only accumulate. Probably a pain, right? Then people come up with accumulator plus address register. And now you have what we call general purpose register. Every register can be used for any purposes. So now it's easy to use, easy to manipulate. And in, say, Intel IA64, you have 128. Okay, awesome, right? Or in the traditional x86, you don't have as many, right? You have those ECX, blah, 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 to R16. That's it, right? And so another thing is addressing mode, right? Which define how do we obtain the operand. For example, same thing that haunt you back in system skill, right? These absolute addressing mode means that I would treat number 10 here as a flat address. Absolute addressing mode is that number is an address. Register indirect means that I'm going to use the address represented by register. That becomes my address. Displays or base, I'll have the offset plus the register value. Right. So you see in the same example from x86, so I'm going to skip through this really quickly. Basically, you can have different way you can go get your address. You can just put in a number. You can put in the value inside the register or the combination of these two. Right? So that's the addressing mode. Each ISA will have its own definition, so be careful when you program. Read the manual because the manual tells you exactly how do we use the address. And the trade-off for each addressing mode is different. So it reduces the code size. For example, sometimes if you know that you're gonna go from A0, right, to A of 10, the array, you can say, I'm gonna put the offset to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that's it, right? You stick with the same register value. One instruction, you're done. Some access are better suited in certain mode. For example, array access is nice when you do just 0 is your A0, and then offset is 0, 4, 8, 12, 16, blah, 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 right? Pointer chasing is probably something that just load a register value, right? Sparse data means that a set of data that has a lot of zero, right? When you have a lot of zero, you basically skip the computation. If you do the multiply, right, for example, it would benefit each types of addressing mode. What are the downsides? The downside is when you need to write the compiler, think about it. Compiler will, by some magic, translate your code to assembly, right? So if I give the compiler 10 different options, it means that if I'm an engineer that have to build the compiler, I'll hate you. Because it means I have to figure out which one is the best. Which means I have to figure out the algorithm to find which one is the best. Well, I mean, I probably hate you and like you at the same time because it give me the job to actually build the optimization, right? So it's awesome, but it's also make things more complex. So it will mean that compiler has to be way more complex to translate your program to work with these addressing mode, right? Also, more work from the hardware side because I need to make sure I support every type. There has to be certain piece of hardware to support every single types. All right. So what else are the elements that I haven't talked about? Things like interface with interrupts IO. Yay. Right. How do we do memory map IO? Right. Some region of your DRAM can be by default talk to your hard drive directly, make it faster, basically. You can have special instruction that handle different IO devices like keyboard and mouse, right? Calling this instruction allow you to interact with this IO. So the ISA would specify that. You can also have the part that you have to specify, okay, if this bit is set, or if you have this instruction, this is from the user versus the supervisor or the OS or the kernel, right? It tells who can execute what, essentially. Exception and interrupt handling. This is also specified in the ISA. For example, MIPS ISA, which you see in a bit, will have the syscall instruction that takes in the number. The number represents the signal, right? Think of it as sigint, sigkill, right? Those kind of signal. It tells you the procedure to follow when something's go wrong, right? What if you have external device request something, right? Or if you have, like, sometimes you have the vector versus non-vector interrupts, the ISA would specify how do you want to be, how should the interrupt be handled. It would tell you how to manage your virtual memory, address protection, right? And now that we are done with the element of the ISA, the next thing is a recap of system skill, which means that instruction has different classes, right? You can have compute instruction that process the data. The basic element of this is I take the operand, I compute, I store it back. Right? That's it. That's the first class. Second class is anything that relates to the data. How do I get the data from the main memory, store them in the main memory, deal with I/O? The third type is control flow, if else loop, right? Change the sequence of where you run things. So these are the three types, and these are the core things that will actually matter for performance, right? So if I have a program that has a lot of data movement, do I want to get a better CPU or do I want to get a better memory? Again, the question is, if I know my program has a lot of data load and store, well, let's say I have limited money, right? Do I upgrade the CPU or do I upgrade the memory? Probably the memory, right? You might want a faster memory. You might want to change your algorithm. If you know, okay, I have no money, I can't buy anything. But somehow my program always go to memory. Well, let's change the algorithm so that it doesn't go to the main memory as often anymore. Maybe use the cache, right? So these are things that matter, right? There's also a way to deal with memory in the sense that a load store machine versus memory to memory machine. Load store architecture means that something like x86, I brings the data into my register. Right? The key is here. Load the data in the register, compute, and store it back. Store it back. Memory to memory means that somehow I want to open up the support for me to copy this location into another location directly from one memory location to another memory location, right? So many of the sysISA also have that option. You skip the compute part, just do the copy, right? So what are the trade-off? So let's say you want to copy one array to another. It might be good to have the memory to memory architecture. If you do a lot of processing, then load store architecture might make sense, right? And now here's a new thing, instruction length. Remember in our system skill class, each instruction take different number of bytes. Some of them with 1 byte. Even with your lab, this assembler, right? Some push takes 2 bytes. Some of them is 4 bytes, right? So that's the instruction length. Some ISA has fixed length. Every single instruction is say 4 bytes, 32 bits. It's a fixed length, easier to decode, decode, easier to decode. What does decode mean? Decode means it's a process where I see the bit pattern and I figure out what is that instruction. So if I know it's going to be 32-bit, why is that easier? Why is it easier to decode if I know it's going to be fixed length? Let's go back to your lab 3 and system skill. What is the most annoying part that I got a lot of questions about? Yeah, it's easy to find out how many bytes do I have to figure out to decode, right? The first thing is, okay, do I fetch 2 bytes? Or do I get the first 3 bytes? Or do I get the first 4 bytes? Right? Yeah. So basically, if you have a fixed length, you can imagine this would take care of that problem. Simple, right? It also allow you to easily tell where's my next instruction, right? So if I can tell where's my next instruction, if I can tell where's my next 2 instruction, I can go grab the first 8 instructions, right? I guarantee I know that it will be there. So it means that you can process multiple instructions at the same time easier, even have a fixed length, right? But let's say it's a 32-bit machine with a code size. Each instruction is 32-bit. It means that some instruction might not need the whole 32 bits, right? So your code can be bigger. your code can unnecessarily becomes bigger. And it's harder to extend. This is quite important. Why is that the case? So let's say you have the version 1 of your ISA and you launch it. Yay, it's a success, right? And then new customer come in. Like, oh, I want a special instruction. Can you add it in? And you're like, oh, I have no room for a new opcode, right? So for example, over here is from the RISC-V instruction set is 32-bit. But the way RISC-V is defined, they carefully design it so that you can extend. But let's assume, right? The opcode is full. The whole 7-bit opcode is filled. It means I can't extend. I cannot add any more instruction than this, right? So it's going to be harder to extend. And here's one example of really, really popular ISA that has fixed lengths, right? So here's the RISC-V integer-based instruction format. So this is only for integer. You can have a variable length. So you've seen that before in x86, right? You have compact encoding. So your code size is likely to be smaller. It's going to be harder to decode because you need to figure out, okay, do I fetch 1 byte? Do I fetch 2 bytes? Do I fetch 4 bytes for my instruction? For example, here is my x86 3 bytes versus 2 bytes of the same instruction VEX, right? You can go check the developer manual. With this, what is the first thing I have to do? It's the same instruction, but I don't know how many bytes do I fetch. So what's the first thing I have to do to check? You first look at the first byte, right, and check this one. Check the value, right? So even before you get to process the instruction, you have to process the bits to figure out what the heck is this instruction and how many bytes do I have to fetch. If you see 100 at the end, it means you get the next 2 bytes. If you see 101, oh, okay, I just get 1 more byte. Yay. Right? And if by accident you get 2 more bytes, the whole thing crash, right? So you need to make sure it is done correctly. This is the part where we call it decoding. Is decode the instruction into the actual operation. Oh, so the question is, can we detect the offset bits position? So it depends. So there are techniques in hardware that you can kind of look it up, right, ahead of time. You look it up ahead of time so you can get this instruction as fast as possible, put that in the buffer. So you know, okay, this instruction is coming up. And in the meantime, you run your program. So that's one of the more common techniques. The instruction is being filled into what we call instruction window. It's a buffer that store every single instruction you have fetched so far. Fetching instruction, as I said, means I go look up that address, get the instruction. So basically it means that I'm going to go ahead of the schedule, look at future instruction, put that in my buffer, right? So here's a trade-off. So a uniform decode where you have a fixed size instruction, you have the same set of bits that correspond to the same thing, right? It's easier to decode. It means that your hardware is really, really simple, right? And you can fetch 10 instruction ahead of time, 15 instruction ahead of time. You know exactly where the next instruction is. For a non-uniform decode, it's more compact for sure. It's easier to extend because, yeah, if you run out of opcode, fine, I'll add more bytes. It is as simple as that. I'll add more bytes. But it's gonna end up complicating your decoding logic because every time you want to decode what is that instruction, you actually have to add transistor and logic gates. Right? You need to add the actual thing that performs the task in the hardware, right? And now that we are actually super close to the finish of the lecture before we go to in-class exercise, I'm gonna talk about what we're gonna learn for these assignments, for the in-class assignments. We'll do everything that involve MIPS R4000. Your project has nothing to do with this. It's in C, so it should be a lot easier. These are exercises that are based on more of the computer architecture side of things. This is a lot simpler than x86. It's a RISC processor. It's simple. It used commercially back in the day. Fun fact, if you own PlayStation 1 and Nintendo 64, they use MIPS. They use MIPS. And the later version of MIPS architecture is also used on PS2, actually. And if you go and attend like a full-blown architecture class in many university, this is typically used as the go-to ISA because it's simple and it's clean. It's actually really, really clean. The full details is available in this book. I believe the links still work, but here's the gist of it. It has 32 register, 32 register. Has a separate program counter. So it's 32 register with its own separate program counter and status register. Status register is basically it checks if the instruction result into things like 0, it carry the bit over, is it negative, and things like that, right? It has the physical memory that divides into 2 chunks, where your program is, which is referred to as the text, and where you store the data. And when you store the data, there's the stack and the statically allocated space, like an array, right? And the first thing for the exercise, I'm gonna ask you to download the simulator. So that is available. It's gonna look something like this. You can actually write your code, right? Put the code here, load the data to your memory, and then run the code. You can run the code and you can see the actual thing that happened on all the register. So it would tell you, okay, if you go through the code line by line, what happened when you run it to each of the register and what happened to the memory. So this is code, register, memory. So that's why it's nice. There's a simulator which is available here. Feel free to install them. If you want me to install in Syscale server, let me know. I might. You can definitely install this on your local home directory in system skill. This is what I recommend you to do. I guess I can make it in the everyone can access a folder, but I feel like might be a good idea for you to basically build the simulator on your home directory. It should not be hard. It also has a Windows, Mac OS, and Linux version. So if you want to play with that, feel free to. The manual of how to do that is in this page. And then for the in-class exercise, I want you to do something. Oh, it doesn't support M1. This is for a different architecture. It's not ARM. Oh, you mean it doesn't work on the M1 processor? I don't know. You can try. I guess if you can compile, it should work, but I'm not sure. It might not. Oops, my bad. So basically, what I want you to do for the in-class exercise is, well, sorry, pen. I want to write a function that add 2 numbers together. Basically, you can assume that the data would be in these address or the data would already be preloaded to a certain register. Write a function to just add those 2 numbers and see what changed in the simulator. Basically, it's just play around with the simulator. Uh, that's all for today's lecture. We have about 20 minutes left. I'm gonna be moving to Discord like usual. Any questions before I move on to Discord? By the way, project 3, do you want it to come out before or after the project 2 due? One question for you guys.